Example 84. The distance a toy car travels on a single charge is normally distributed with an average of 3,000 yards and a standard deviation of 50 yards. What is the probability that the car will go more than 3,100 yards without recharging? All right, so when I read the problem, the first thing I need to do is see this phrase, normally distributed. So it's saying the distance the car will travel is normally distributed. That implies the bell curve, so I should draw a bell curve to solve this problem. That's going to be my very first step. I draw a bell curve. Now once I have the bell curve drawn, I will proceed to draw a z number line. And then because this problem does not have a standard normal distribution, it just has a normal distribution. It has a different mean and different standard deviation, in other words, than the z-curve. The z-curve has a mean of 0 and a standard deviation of 1. So this is obviously a non-standard normal distribution. That's kind of a mouthful, huh? It's a bell curve, in other words, that it doesn't have a mean of 0 or doesn't have a standard deviation of 1. Whenever that happens, you need to create an x number line that puts the variable that we're interested in this problem on that number line. So in this case, we're interested in the distance the toy car will travel on a single charge. Well, on average, it says that that value is 3,000. So I'm putting the mean on the drawing where it belongs. That's where you put your mean. Your standard deviation, I would like you to label in this upper corner. They gave it to us to be 50. You want to have it at your fingertips. The mean is always in the center on the curve, so that's easy enough to remember, right? You can even write the symbol mean underneath it if you want, but make sure that the standard deviation is labeled in the drawing so you don't have to keep referring back to this to finish the problem. Now, the last thing we need to do for the drawing is to put the number that they ask us about on the curve. So they say, what's the probability that the car will go more than 3,100 yards without charging? So 3,100 is to the right of 3,000, right? So on this x number line, important that it's on the x number line, we put that value. I draw a line where that value is located, and then I think about what probability I'm looking for. I'm looking for the probability that the car will go more than 3,100. If x represents the distance that the car will travel, I'm looking for the probability that that distance will be greater than 3,100. So greater than 3,100 is to the right, right? Remember my rule, I said if your variable is on the left, that will literally point to where you need to shade. So greater than 3,100, there it is. Now from there, you want to convert that into a z-score, because here's the problem. If I want to find that area and it's on a bell curve, I'm going to need the standard normal distribution, that chart that we have, that z-score chart. And that chart will give us areas under the bell curve. But that chart does not have numbers like 3,000 or 3,100 on it, because that chart is a z-chart. So the only step extra that I have to do in this section compared to what we were doing earlier is I need to convert this 3,100 into a z-score so that I have a number that I can look up on a table. I don't have a table for distances that a toy car will travel. I only have the z-table. So I need to first use the z-score formula to convert this guy into a z-score. That's just a simple side step, right? I'll just do that off to the side. I'll say, hey, look, the z-score is the number I want to convert minus the mean over the standard deviation. I have the number I want to convert, I have the mean, I have the standard deviation. So if I plug that all in, I will get 3,100 minus the mean of 3,000 divided by the standard deviation, which is 50. That'll give me 3,100 minus 3,000 is just 100. And if I divide by 50, of course, I get 2.00. Remember, that is my z-score. So if that's my z-score, it belongs here on my drawing. So what we're saying is, hey, 3,100 in the z-scale is 2. They're the same number, just in different scales, right? This is a distance. This is what that is correspondingly as a z-score. That distance is 2 standard deviations above the mean. So now that we have the 2, we can go to the z-chart and look up 2. But be aware, when we look it up, we're going to get the area from here to here. That still hasn't changed. The z-chart only gives us the area we're looking for. Sometimes you're so wrapped up in the work you've done to get to this point that when you look up your area, you just automatically call it the area in the shaded region. But remember, the chart doesn't know what you shaded. It only knows if you ask it for 2, it gives you the area from 2 to the center. That's not the area we're looking for, so we'll need to find the tail area by using one of the techniques we learned in the earlier section. So let's go look up 2 first, get this area from the table, and then we'll come back and find the area we're actually looking for. Okay, so we're looking up 2.00 on our z-chart. Let's move our table down so we can see it in this leftmost column here, right? Okay, so I see the 2.0, and if I go over to the 0 position, that's the first position after this column begins, and it's 2.00, we get 0.4772. 0.4772. Okay, so we found the area to be 0.4772, but that's the area here in the white space. To find this area, we're going to have to use that trick where we say, hey, half the curve is 50%. If I take away the white space in this half, I'll be left with the shaded space. So 0.4772 taken away from 50%. Again, if we do a little borrowing here, old school borrowing, right? We get 10 minus 2 is 8, 9 take away 7 is 2, 9 take away 7 is 2, 4 take away 4 is 0. We get the answer 2.28%. So let me just rewrite this statement a little bit. I'm going to say the probability that x is greater than 3100 is the same as the probability that z is greater than 2.0. That's what we just showed, right? That these two probabilities are equivalent. And if I do that, the answer works out to be 0.0228, which we just said was the same as saying 2.28%. And that is the probability that this little girl will be able to drive her car more than 3,100 yards without going back for a recharge. So it's not a huge probability, so she better be careful and make sure she keeps it charged before she goes too far on it.